I'd like to talk about how we go about calculating the electric field for uniform charge distribution. So when a set of charges are uniformly distributed throughout some geometrical shape, what does the electric field look like? And the book goes through a four-step process for doing this. Excuse me. Where first you break the distribution into pieces so that you can make it look like you're just calculating the superposition of point charges. And once you've broken this up into pieces, what you can do is you can write an expression for each piece that algebraically looks the same. So the equation is the same, although there's a variable in the equation that's changing as you add each new piece into the superposition. Once you have those two steps done, then it's just a matter of adding up all the pieces or calculating the superposition, and then you would check your result to make sure that it makes sense. So let's see how this works. So the simplest one is a one-dimensional system. So say you have a thin wire that you create an excess of electrical charge. So in this case, we'll say that we remove some electrons and it becomes positively charged. And in the discrete picture where we have point charges, it looks like this image on the left-hand side where there's a uh, long line of charges, and you can think of them as individual uh, protons, for example, so that they're positively charged. And uh, in the continuous limit, that becomes such a long, thin wire that has electrical charge that each individual charge is so small that you can think of it as a continuous distribution of charges. And so in this case, the red charge here, it could be multiple charges or it might be a single charge. It doesn't really matter, but it takes up some geometrical space in the long, thin wire or rod here. And so that small amount of charge, which they're calling delta Q, takes up some geometrical space, delta Y. And it doesn't matter where on the rod you choose. If you choose the same delta Y, there would be the same amount of charge, delta Q, in that section of the rod. So if I look at the same delta Y, say down here, then there's going to be a delta Q in there. And another way to say that is that the density of the charge in this long thin rod is uniform. It's the same density everywhere in the rod. And so that's going to be really important. That's actually one of the trickiest parts of solving a problem like this, is recognizing that delta Q over delta Y is a constant value for this, and we would call that the charge density. And something that is really important to realize is that if you were to consider the entire rod, so I'll just draw the entire rod and think about all of the charge that's in this long rod, there's some total amount of charge in there that's distributed over the length of the rod, that's L. And so the charge density is also the total charge Q over the total length, which is equal to the amount of incremental charge over some small increment, delta Y. And that's because we're considering this to be uniformly distributed, so that's just a constant. And so that's going to become really important later. That's one of the trickiest pieces to solving this problem.